The next set of examples has us calculating equilibrium concentrations when all we know is the constant and the initial concentrations or the initial pressures. They're going to talk us through a three-step process and involves the quadratic formula, of which I happen to have on my calculators. I don't ever solve it, so if you happen to have that or ask me to download that to your calculator, you probably have it already. So let me just be sure on my calculator I say that. Under programs, I have the quad. So that's going to be my typing in, oops, I didn't mean to do that. Typing in for programs, it's going to ask us for the value of A, the value of B, and the value of C respectively on our quadratic equation. Alrighty. So with that in mind, let's take a peek. The series of slides will go together. It'll be one example, just one step at a time. So let's take a peek at what the problem is asking. Let's suppose we have a reaction. Iodine plus chlorine is in equilibrium with 2 ICLs. The value for this Kp is given as 81.9. We know the initial partial pressures are at 0.1 atmospheres. So right off the bat, I'm not liking the fact that these are brackets. These are partial pressures. The partial pressure of iodine, the partial pressure of chlorine, and the partial pressure of iodine chloride, ICL. Not brackets, they're pressure units. We'd like to know the equilibrium values. It's all, we know the Kp, we know the initial concentrations. First we want to do, because it's charged with concentrations or pressures, if you will, for both reactants and products, we have to decide, are we heading to the right or are we heading to the left? The reason I need to know that is, if it's heading to the left, products are going to be consumed. If it's heading to the right, reactants are being consumed. So let's just quickly check with these values, calculating what's called a Q, a reaction quotient. The reaction quotient says, let's plug in 0.1 squared because of the coefficient times 0.1 over 0.1. You get an expression, Q is 1. Q is 1. The Kp, recall, was 81.9. So Q is coming out far smaller than K. And so therefore, the reaction is proceeding forward. We need to make more product to get that reaction quotient larger. As reactants go to products, reactants get used, products get made. So here's what we'll say. Let's say to the value of X, the iodine is going down. To the same value, because it's a 1-to-1 ratio, the chlorine is getting consumed to the value of X. Products get made, look at the coefficient. Twice the number are going to get produced, 2X. So at equilibrium, 0.1 minus X is the concentration or partial pressure there of iodine. 0.1 minus X for the chlorine, and 0.1 plus 2X, representing at equilibrium the value of iodine chloride. That's what we have filled in on the next page. We can just pick up the problem there on the next page. Reactants got used, product got made. This 2 comes from the coefficient of the 2 up above. Alrighty. So if reactants got used, the coefficient of 1 representing the value of X. 0.1 minus X times 0.1 minus X. And here, the concentration of 0.1 being made plus 2X. Now, my friends, it becomes an algebra problem. We're proceeding to the right, product over reactant, so we know Kp is found by taking the partial pressure of our product, iodine chloride, squared, times the partial pressure of each of our reactants multiplied together. We're squaring the top because of the coefficient, and down below, 0.1 minus X times 0.1 minus X, the values at equilibrium of each reactant. Square the top, divide by the bottom in that expression. So 0.1 plus 2x squared, and since this is written identically, that's what they've simplified here, 0.1 minus x squared, although I would probably have to FOIL and pull out the values. So now it's you and your calculator simplifying that equation. I recommend a whole lot of quadratic equation simplification and use that expression a, b, and c. If you can write out your equation in terms of a quadratic formula, plugging in the value of a, b, and c, quite easily you can solve for x. Remember that when you use the quadratic formula, one of the values will be tossed out because it makes no sense. Generally, it comes out negative, and you can't have negative concentration, so that's the one I toss out. Alrighty. So, how good are you at algebra? 0.1 minus x times 0.1 minus x. Step 1, I would FOIL that. First, outer, inner, last. Step 2, I would distribute the 81.9. And that brings this side up here. I'd end up foiling this as well and get it to the form of the quadratic expression. We need the value of a, b, and c to plug into the quadratic formula to solve for x. Ax squared plus bx plus c equals 0. Where the x squared, that number in front, will plug in for a, the b for the value of x to the first power, and the number by itself will be the value for c. Use your quadratic equation formula and solve for x, tossing out the one that's negative. Now, if that's something that's not algebraically familiar to you, we can sit one-on-one and do that, but I'm not going to record myself working out a quadratic formula when I prefer just to use the program right here on my calculator. Alrighty. Trick here then is just getting familiar with how to distribute. Alrighty. So once we solve for x with the quadratic formula, x gets plugged right back in up above to solve for the equilibrium concentrations. 0.1 minus x, the concentration of iodine at equilibrium. 0.1 minus x, the concentration of chlorine at equilibrium. 0.1 plus 2x would be for the product iodine chloride. 0.1 plus the value of 2 times x. So using your quadratic equation,